Hello, my name is Hieu, and today we will talk about real-time street parking sign detection and recognition. I worked on this project with my colleagues Yin and Jiayu under the supervision of Professor Hu and Professor Cheng. So what is the motivation for us to work on street parking sign detection and recognition? Although similar to traffic signs, street parking signs can get really complicated. Here is one of the more extreme examples. This is a problem for drivers to interpret when every second matters on the road. So having an automated system to detect parking signs and generate rules is essential for drivers. Furthermore, this benefit would greatly expand to the development of autonomous driving. And although practical, street parking sign detection and recognition is still a relatively unexplored area, on top of the lack of public data. So for our project, we want to address these problems by introducing our own dataset of parking signs across multiple cities around the United States and study the feasibility of the commonly adopted object detection methods when applied to our task. To work on this, we must define a detection pipeline, and ours looks something like this. We start with a raw image taken from the user's phone or from a frame in the video stream, pass it to a sign detection unit which will locate all the signs and crop it out of the original image. Then, a symbol detection model will identify all the symbols on the cropped signs. From there, we can start generating parking rules and inform the user appropriately. This pipeline consists of multiple components, and our work focuses on sign and symbol detection. Because of that, our dataset is divided into two parts. First is the dataset for parking sign detection. It contains 4,191 street-level images of parking signs on a background. About half of them were taken by hand, and half of them were frames extracted from dash cams. And as you can see, signs in these images have different shapes, and they were taken in different situations, such as different shooting angle or lighting. The second part of our dataset is for parking symbol detection, and this set contains 3,369 crop parking signs. For the moment, we identified 27 types of symbols that would be useful for parking rule generation, including text, no or allow parking, handicap, arrows and tow away, and etc. For our experiment, we use our dataset to train and evaluate the sign and symbol detection models separately. The object detection architecture we implemented were RetNetNet, Swin Transformer, and YOLO v5. We focus on three metrics: accuracy, inference speed, and model size, to meet the practical requirements of a real-time detection model. First is the experiment for parking sign detection. Since YOLO v5 offers multiple model size, we use a portion of the original dataset to evaluate the trade-off between them. And according to Table 1, YOLO v5S, or small, is considerably more lightweighted and faster while yielding sufficient accuracy. We then retrained this model to compare with RetNetNet and found that YOLO v5 outperformed RetNetNet by a large margin on all metrics. For parking symbol detection, we compared Swin Transformer with YOLO v5. And although Swin Transformer is extremely accurate, its processing speed is only 5 frames per second, while YOLO returned 98 to 99% accuracy and performed inference 10 times faster. Therefore, in both sign and symbol detection, we observed that YOLO v5 is very suitable for our task. So how do these models work together? We ran a full pipeline on the street-level dash cam footage, where signs are located on one side of the street. And as you can see, that a sign detection model locates all the signs available, and for each sign, we identified all the text or other symbols, translate them to text, and finally generate parking rules. In conclusion, for this project, we introduced a street parking sign dataset with a sign and symbol annotation. And using that dataset, we found that YOLO v5 is the architecture that would be practical for our task in real-time detection. In terms of future work, one pattern that we found while collecting this data is that different cities across the United States can have drastically different style for the same sign symbol, and expanding our dataset would greatly increase the flexibility of our models. Secondly, from the dashcam demo, we can see that a same sign is sometimes not consistently detected across all frames, and that is something we plan to investigate. Finally, text is vital for talking rule generation, so we will evaluate the detection and recognition on this component more extensively in the future. That concludes my presentation. Thank you for listening.